Hello everyone and welcome to this video. Today we will explore a fascinating topic in quantum mechanics, solving the Schrödinger equation for a potential barrier. This fundamental concept in quantum physics illustrates how particles behave when encountering obstacles on the quantum scale. The Schrödinger equation is the cornerstone of quantum mechanics. For a particle of mass m, it is given by phi x, the wave function, Vx, potential, en E, total energy of the particle. Okay, in this video, we want to solve this Schrödinger equation in the case where Vdx it is a rectangular potential barrier. It means that we have Vdx like that doing the representation. So we want to solve the Schrödinger equation for this kind of potential energy. Let us now consider a one-dimensional potential barrier. We are particularly interested in solving the equation for a particle which energy E lower than the potential energy is 0, meaning that it does not enough classical energy to overcome the barrier. So the solution depends on the region. In region 1, x is lower than 0. In this region, the potential is 0. So the Schrödinger equation simplifies to where the general solution is a combination of traveling wave where E1 in region 2 inside the barrier the potential is V0. So the Schrödinger equation takes the form where K equal in this case the general solution is Now the last region 3. Once again, in this region, the potential energy is 0, so the Schrödinger equation remains. And the general solution for this differential equation is to connect this solution, we apply the boundary condition. First, phi x must be continuous, and secondly, the derivative of f, which x must also be continuous. Using this condition at x equals 0 and x equals a, we can relate the coefficient e1, b1, e2, b2, e3, and b3. So the continuity of phi and derivative of phi imply this system of equation phi1 at 0 equal phi2 at 0. And then this implies okay. It's pretty long. So we have a system of 4 equations with 6 unknown which cannot be solved directly. To simplify it, let us analyze the significance of this coefficient. Let me make a scheme. So we have the barrier, and in this part In this part, the equation is the wave function is a exponential of kx, and in this part the wave function is on type. So we assume that the particle originally the particle originate from the region 1, this region, and it's emitted from minus infinity, corresponding to the term a1. Part of it is reflected, representing the part b1, while another part is transmitted into the region 2, so represented by the term R2. A portion of the wire is reflected at the exit of the region 2, corresponding to the coefficient b2. At the remaining part propagate into the region 3 as h1. Since there are no particle source at plus infinite that will propagate from the region 3 back into the region 2, we set b3 equal 0. So this reduces the number of unknown to 5. To further simplify, we normalize the source term by setting a1 a equal 1. So the new system is 1 plus b1 This implies Now we solve the boundary condition. We multiply the first equation, equation E1. We multiply the equation E1 by E small k divided by big K divided by big K. And we sum the equation E1, which is E1 and E2. Also, we multiply the equation E3 by minus E small k divided by big K, and then we sum the equation E3 and E4. So we get this new system of equation. There we have E k divided by E1 plus E2. This gives the equation 1 plus E small scale to big K plus minus 1 plus EK big divided by big K. And the second equation is minus EK plus by E3. We call this equation E5 and this E6. So from the equation E6, we express B2 as E small k to big K exponential to K A. Now we substituting this into E5, we obtain E2 equal to E small k to big K 1 plus square and this is equal to E small k capital K E K divided by 1 plus 1 square where alpha it's this quantity. Yes, this quantity we call alpha. We call alpha. So similarly solving for b2, we get b2 equal alpha 1 minus e k capital K exponential of 2 k a. So now by substituting e2 and b2 into the equation e1, the equation e2, we can find b1. So we have b1 equal to alpha 1 plus k square k capital square minus 1 for exponential to 2 ka I k divided by 19. Also similarly, by substituting e2 and b2 into the equation e4, we can get e3. So we have e3 is more simple. We have the expression of e3 more simple. We got e3 equal alpha exponential k minus ek. So thus the solution in all regions are determined solely by the problem parameter. Okay, we have resolved the Schrodinger equation for all of the three regions. Now we want to discuss about something. So the coefficient b1, the module of the coefficient b1 correspond to the transmission this coefficient correspond to the reflection. So b1 correspond to the reflection coefficient, and the module of E3 is the transmission coefficient. You can see bit A, bit T. Observing the transmission coefficient E3, we note that it's non-zero even though the energy of the quantum particle energy E is lower than the potential barrier V0. This phenomenon observed in quantum physics is known as the tunneling effect. This phenomenon describes how a quantum particle can traverse an energy barrier with an energy lower than that of the barrier. So this phenomenon is analogous to optical transparency in optics. This quantum property is notably used in construction of scaling tunneling microscope. This thing is used for STM, scaling tunneling microscope. So Thank you for watching this video and see you for another topic.